I did supply you with a note sheet over this material. It's not that each of these things has to be shown, but it is a great way to kind of organize your thoughts as you attack a problem. Now, ignoring what is below that, when you read this problem, it will seem very overwhelming. And I get that. And so kind of breaking it down little step by little step as we work our way through this can really help you tackle something that is overwhelming. So let's start, and this first one's not too bad. The second one, as you read it, gets a little bit even more overwhelming just because they throw a lot of stuff at us. So a hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. At the moment, the rangefinder elevation angle is pi over 4. The angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? Okay. So a lot of information is thrown at you in these problems. The very first thing you need to do is just give yourself a visual representation of what is going on. And one of the big things that happens when we make these visual representations is people want to put too much information in them. But the only information you can put in this picture is going to be something that will not ever change. Okay? So if we can kind of figure out what's going on here, we've got a hot air balloon, and a hot air balloon would start at this liftoff point. So here's my liftoff point. It goes straight up in the air to some location, right? It lifted off above a level field, and it said that we've got this rangefinder over here. So here's my rangefinder looking up at that balloon, right? And that rangefinder, it said, was 500 feet from the liftoff point. It talks about the angle of elevation. So this would be an angle of elevation from the horizontal line up. Okay. They give us a bunch of numbers. And of the numbers they give us, the only numbers we can use, if any, are numbers that will not change as time goes on. So think about the sides and angles of this triangle. As the balloon starts here and starts rising, our angle would be changing, wouldn't it, as it goes up? This side length, the height of the balloon, would be changing as it goes up, right? Is there anything in this picture that is not ever changing the whole time this situation's going on? Right? That 500 feet, that's never going to change. It doesn't matter where the balloon is. As that rangefinder is finding it, it's still going to be 500 feet the whole time, right? So I can label the 500 in my picture that will never change. It did talk about the angle of elevation, but that's going to change. And so what I would want to do for myself is kind of indicate that that's something in this problem, but it's a variable, right? Varies as the problem goes. So yes, we are going to look at our angle of elevation, call it some sort of variable. Theta is usually what they call angles in calculus, okay? Some sort of a variable. It's also talking about the height of the balloon, right? How fast is it rising? How quickly is this height changing? So it's talking about this height here. So I kind of label the things that they refer to in the problem or have anything to do with my problem with variables unless that thing is not changing, and then I can put that number in there. Any questions on the picture part of it so far? After we've created a picture for ourselves, and a lot of times it's going to, well, all the time, it's going to be some sort of geometrical shape, whether that's a two-dimensional triangle. Eventually we'll get into some three-dimensional shapes, but we should be able to create some sort of equation that would put all of those pieces into play. And our pieces are a side length of 500, an angle here, and a side length of h. Okay? So knowing what we know about right triangles, what type of situation would include those three pieces of information? What'd you say? Tangent. A trig equation. A trig equation is going to include angles and sides of our triangle, right? So when that is the case, and basically, guys, we're going to find out that there's really just two situations that are going to happen. If it includes angles we're probably talking a trig equation that we could set up. So then we have to think through SOHCAHTOA. Here's my angle, opposite, adjacent, or hypotenuse. Opposite, adjacent, or hypotenuse. Adjacent. So which is our trig function, which Kyan already told us, that uses opposite and adjacent is what I would be thinking through right now. And he said tangent, right? So the equation that I can set up that would relate all of these pieces to each other is that the tangent of our angle theta is going to equal opposite over adjacent. Any questions so far? Okay. Now, in this equation, because I know where this is going and we're trying to find the rate of change of our height, how fast is it rising, I'm going to solve this for h because I can. It also makes the derivative a little bit easier here. And we don't have to. It doesn't change anything. But if I solve this for h, I can multiply by 500, get 500 tangent theta equals h. Okay. We are always going to be talking about rates of change. Related rates is the topic, this section. So rates of change. Well, rates of change come from our derivatives. And so now what we're going to do is take this equation, this function that we just created, that relates all of the things that are in our picture together, and we're going to look at its derivatives so that we can see not only what are those variables, but how are they changing over time. And so what we'll do is we'll take our derivative with respect to time. So these will all be over dt as time changes. So let's talk about how to do that. Let's look at this first side. 500 is just a constant multiplier, right? So that it'll just be a constant multiplier of our derivative. What is the derivative of tangent? Secant squared. This is a chain rule because the inside variable is theta, which is not time. And so then we have to follow it up. Just like when I took the derivative of something that had a y in it, I had to follow it up with dy dx. Well, now we're doing all of ours with respect to time. How is it changing over time? So I would follow this up with d theta d time, d theta dt. So as we go through and take our derivative, every variable, because none of these are time, will be followed up with a derivative with respect to time. And then move over to the other side. Okay, now if I were to do my power rule here, the derivative of h is 1 times dh dt. How is our angle changing over time? What is the rate of change of our angle? Right? That's a phrase for that, the rate of change. What is the rate of change of our height? You see what those are standing for as we do this? Okay. Over time. How is it changing over time? As we look at this equation, we have 1, 2, 3 unknowns in that problem. You have one question. One of those 3 things is going to stay an unknown because that is the question. So if we go to the end, it says, how fast is the balloon rising at that moment? Which of those 3 things, which I think I already told you, which of those 3 things represents the how fast is it rising? dh dt, right? The change in our height. So this is going to stay an unknown. That is the question they are asking us. What is the rate of change of the height? How fast is it rising? The other 2 things are the angle and the rate of change of your angle. All other unknowns, I need to go back to the situation and find that information somewhere hidden in those words up there to fill in for theta and to fill in for d theta dt, right? Our rate of change of our angle. And we see those. At the moment, the rangefinder's angle, there it is. Angle is pi over 4, angle being theta. So I go and plug in pi over 4 for theta. The angle is increasing at the rate of, there's our rate of change of our angle. Rate of change of our angle is the d theta dt. So then we would put in for d theta dt, 0.14, and we already talked about that dh dt is our unknown. That's what we're trying to figure out. And then I grab my calculator. And I make sure my calculator is in radian mode, and that I know how to find secant on my calculator, which is 1 over cosine. Okay, if I want to do secant squared, first of all, secant of pi over 4 is the same thing as 1 divided by cosine of pi over 4. That squaring it here is the same thing as squaring it on the outside of that. And as I type this in my calculator, that's how I'm going to want to do that. Figure out what this is and square that result. Okay. Times 500 times 0.14. What is it? All right. That is correct. It is 140. Are we all getting 140? Okay. Now, the last step up there says interpret your answer correctly, either in a sentence explaining or with labels explaining is a huge part of this. So how am I supposed to figure out my label? Guys, first of all, you could let this be your guide. The change in h over the change in time. Well, what is our height being measured in? Feet over, what is our time being measured in? Minutes. So it would be in feet per minute. 140 feet per minute. Labels will be very big on this. Questions? Okay. So that's kind of our plan of attack for all of these. Draw a picture, figure out the geometric shape. What type of a function can I create that involves all of the variables that are going on in there? Take its derivative, fill in my unknowns. There should be one unknown left because that's what I'm solving for. All right? So let's do one more example here. This one I think is very overwhelming as we read it and get started. It says, a police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now moving straight east. When the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determined with a radar that the distance between them and the car is increasing at 20 miles an hour. If the cruiser is moving at 60 miles an hour at that moment, what's the speed of the car? That is a lot of stuff going on in that problem, right? So let's break it down. Let's draw a picture of what's going on. So it starts out talking about a police cruiser going towards a right-angled intersection from the north. So again, if you kind of think cardinal directions here, this would be north, south, east, and west, right? So our police cruiser is sitting up here on the north, heading towards a right-angled intersection, right? Right-angled intersection. The car that it's chasing already got to that intersection, turned the corner, and is heading east, which is why I drew it this direction. So here's the car it's chasing. I can see the shape happening here, isn't it a triangle? Because it talks about at this moment in time, the police takes a radar, points it at that car, and says that this is changing at 20 miles an hour, right? Isn't that what it says? The distance between the police and the car, which would be this guy right here, is changing at 20 miles an hour. We're supposed to figure out how fast that car is driving. Okay, now, of all those numbers, talks about this being the police cruiser is 0.6 miles, the car is 0.8 miles, this is 20 miles per hour, 60 miles per hour, the police, ooh, this is kind of important. The police is driving this direction, right? And the car is driving that direction, okay? It is going to be important to us in just a minute here. Which of those is never going to change? They're all changing, aren't they? Everything is changing. It's getting closer to the intersection. That car's driving farther from the intersection. This is changing at 20 miles per hour, but isn't he going to have to slow down to turn the car? Like, everything is changing, isn't it? So of those numbers, none of them can be labeled on our triangle right now because they're all going to change. Agreed? Okay. So we've got a blank triangle right now. But they talked about all of the sides at some point, didn't they? They talked about this distance right here. They talked about this distance right here. They talked about this distance right here. So they referred to all of the sides in our triangle. Well, what is that thing that relates all the sides in a right triangle? I hope somebody just muttered Pythagorean theorem, right? Yeah? Okay. Yes, Pythagorean theorem. So we can create, and that means we just have to name our sides up here. I'm going to call this y because it kind of matches up with my y-axis, x-axis. I don't have an axis for this one, so z. Okay. But I know that the relationship between those sides in my right triangle is the Pythagorean theorem. X squared plus y squared equals z squared. Right? I don't care if you call them A, B, and C, whatever you want to call them. We got unknowns that are all changing. Okay? So I now have an equation that relates all of that information together. So I can go over and start my derivative. Those are all just a power rule, all changing with respect to time. So it would be 2x dx dt plus 2y dy dt equals 2z dz dt. Okay, now this is not going to impact your problem. However, it can make it a little simpler. Let's go back to some algebra, some nice easy algebra. If I had handed you the equation 2a plus 2b equals 2c, what would you have done? Take away the 2, right? Divide everything by 2, factor out, just get rid of the 2, right? Isn't that just a plus b equals c? Okay, isn't that kind of what we're looking at right there? If they're all multiplied by 2, can't I just divide everything by 2? Yes, the answer to that is yes, you can do that. So you don't have to, and you would not have to. You will see me do that a lot because obviously then I'm working with smaller numbers and I don't have to deal with this 2 in there still. So we could go through and divide everything by 2. So it didn't go away, I'm just solving, right? And then I look at this problem, and I have 1, 2, 3, 4, 5, 6 unknowns in there, right? So we have to identify from those 6 unknowns, x being this distance, y being this distance, x dx dt would be how much this is changing, the rate of change here. Dy dt would be the rate of change here. Z would be this distance. Dz dt would be the rate that's changing. Okay, well, of those, what is the question asking us? What is the speed of the car? So of those 6 options, which one's going to stay my unknown? Dx dt, the rate of change of distance x, right? What is the speed here? So this guy right here is what's going to stay. The other 5, I should be able to fill in with numbers. Okay, so going to fill in those sub-in values from the story above. Let's start reading our story. When the cruiser is 0.6 miles north, okay, 0.6, I should be able to fill that in somewhere. Where does that go? Y, isn't that our cruiser's distance? So I can put 0.6 in here for Y. All right. Of the intersection, and the car is 0.8 miles. Okay, we've got 4 more variables to fill that in for. Which one does the 0.8 go in for? X. And I'm going to go ahead and put in that dx dt because we already talked about, we know that's not changing. The police determined with the radar that the distance between them and the car is increasing at a rate of 20 miles per hour. Okay, is that dy dt, z, or dz dt? Dz dt, right? The distance between them is changing at a miles per hour as a rate. So that's our dz dt. The cruiser is moving at 60 miles per hour at that instant of measurement. 60 miles is dy dt or z? dy dt. We got two things to talk about. Let's talk about this 60 for a second. We have not run across one of these before, but as that police cruiser continues driving, our y value is going to decrease, isn't it? So this is the first time we've seen this, but if the variable that you are dealing with is decreasing, your rate is negative. So yes, it says 60 miles an hour, but it will be a rate that is negative. So we have to come over here and make this a negative 60 miles an hour because it is decreasing over time. The value of our variable there is decreasing over time, which equates to a negative rate. Okay, I have run out of numbers in that problem, and we still have a blank up there. That's an issue. Okay. What kind of a triangle is it? Right triangle. And if one side's 0.6 and the other side's 0.8, and I handed you a right triangle with two sides on it a long time ago, what would you have done? Pythagorean theorem, right? Okay, that's the key on this one. When we are dealing with Pythagorean theorem in our setup, you're probably going to have to do Pythagorean theorem at some point because they're not going to tell you that third side. They figure you can figure that out on your own. So this is 0.6, this is 0.8, this is still our unknown. Do your Pythagorean theorem. Z is 1 mile. Okay. All right, now grab your calculators and solve that for dx dt for me, please. What is it? 70? Does that seem appropriate? 70 what? Miles per hour. How much is our distance changing over time? Miles per hour. Okay, so two big things you're going to get out of this one. First of that is when our rate is of something that is a decreasing value, that we put it in as a negative rate. They are not going to ever give you a rate with a negative number in front of it. They will give you a rate that has the word increasing or decreasing in front of it. And so, like this one said, increasing at 20 miles per hour. So I know that it is a positive rate. They didn't say anything about the cruiser changing at 60 miles per hour, but because of the situation, I knew that y was going to be a decreasing variable. Any questions on this? There is a lot more varieties of problems in this section, and so we will continue to add. We have not seen a three-dimensional object yet. We will get there, okay? Tomorrow we'll jump into a problem with a three-dimensional. It's the same plan of attack. We just have to now think with situations that are three-dimensional. I am going to leave you with this to kind of give you a preview of that. Some hints that we will use is that if I am trying to solve for a particular rate, it is easier to write your function in terms of that variable. So if they had handed me the situation that says we've got a volume of looks like a cylinder, because pi r squared h would be the volume of a cylinder, and that our radius is 3 times our height, and we are trying to solve for the rate of change of our height, dh dt, it's easiest if I were to instead come back and write this in terms of height. Okay, so how would I do that? Well, if r equals 3h, and they tell me that volume is pi r squared h, I can do substitution in for that. And now this is in terms of h. And then as I do my derivative, I will only have a dh dt in there and not have to deal with a dr dt as well. So if you are able to. Now what if they had asked me to do dr dt instead? Well, then I just manipulate this beginning equation. If they tell me that r is 3h, I would solve that for h and plug that into the equation. And now I'm down to a volume equation that only has r in it. And as I do its derivative, it will only have a dr dh. And it is a lot easier to, on the front end, put those in there than it is on the back end. Okay, which you can do, but just kind of giving a little preview of where we are headed with this. We already talked about this. Keep an eye out for negative rates. If your situation is decreasing, we saw that with the car driving towards the intersection. Another situation that we are going to, for whatever reason, in related rate sections, we are filling up and draining a lot of containers with water. I don't know why, but we will fill up and drain a lot of cylinders that have water and a lot of cones that have water. So is the water rising or is the water falling? Makes our rate positive or negative. And so we'll have to pay a lot of attention to that. Like I said, when we get into our three-dimensional shapes tomorrow, we will talk more about that. This is, I hesitate to say this, it's kind of like optimization. It's not. You guys are going to feel a lot better about this one, I promise. But you got to try it, okay? These are not going to happen with you just watching me do these in class and never having gone through a problem on your own, okay? There is a lot more normal plan of attack and a normal pattern to these problems than there was for optimization. You will be a lot more successful when we get to the end of this one than you felt going off of that quiz, which was not that bad. I'm not through them yet, but it's not as bad as you are feeling right now. But you will feel a lot better about this one, I promise, by the time we get to the quiz. Okay, related rates usually goes a lot better. It's a little overwhelming at the beginning. You'll be fine, as long as you do this. Okay, you got to try the problems. Your assignment is on page 255, and again, we will reconvene tomorrow, do a couple more examples. Try again. All right, we done taking pictures?